Welcome to the next lecture on machine learning for core engineering disciplines. In the last class we looked at a variety of metrics, right, parameters that you can define or extract out of a population, and these included the population mean, variance and standard deviation. We also discussed that we can't really work with the entire population because we will not have access to it. So, instead what we do is we derive a sample out of that population and we define all the metrics on the sample, right, and the hope is that with the knowledge of the sample we can extract many of these useful features from there. So, let us see how we can extract these sample properties. Okay. So, right, oftentimes we do not know the underlying distribution, and thus the probability density function PDF of a given data set or population, and thus we cannot determine the population properties. Right. For this reason we have to work with the sample properties, right. Just to refresh you, you know that the expected value of x, which is denoted as mu, is simply minus integral minus infinity to infinity x f of x dx, and if you do not know f of x, then what do you do, right. So, that is a problem, and here in today's lecture we are going to look at sample properties, but I want to remind you that it is possible in machine learning to have generative algorithms, right, algorithms in which you do not really know what f of x is, but you are trying to approximate it and then you try to sample from that particular distribution. So, that is indeed possible in machine learning. We will probably come to it later in the course, but that is something you should keep in mind. Okay. So, in these cases, because f x is not known, we can't compute the mean and the standard deviation and the variance and so on, right. You can define other things like skewness, kurtoses, we are not really discussing those here, right. So, in these cases we can come up with sample metrics, right, and these sample properties are often done with a way to estimate the population properties. So, in this context I will define something known as an estimator. So, an estimator, and it is denoted as theta hat, right, a hat on top of theta, is an expression used to estimate a statistical quantity theta, right. So, for example, you may want to estimate the population mean or population variance. Okay. So, that is the so you define an estimator for that, and obviously an estimator can only provide an estimate, it may or may not be 100% accurate, and in more statistical terms you can define what is known as the bias of an estimator. Okay. So, in statistical terms, one can define the bias of an estimator. Okay. So, this bias, which is denoted as B of theta hat, is simply the expected value of theta hat, right, minus the actual value of the quantity being estimated, right. So, this B is the bias of the estimator, this E of theta hat is the expected value of the estimator, and this theta is the true value of the estimand, which is essentially the quantity that is being estimated, right. Now, depending on how on the value that you compute for the bias, right, there can be two different scenarios, right. One scenario, right, is when your bias is 0. So, B of theta hat is 0, right. Essentially this is only possible if the expected value of theta hat, right, over many samples is equal to theta itself. So, then theta hat is called an unbiased estimator. Right, and the other sort of less desirable outcome is that the bias is not equal to 0. So, this means that the expected value of theta hat is not equal to the actual value, right, of the estimand, then theta hat is called a biased estimator. So, essentially we are trying to get a handle on if we were to find the expected value of the estimator, what value it would take over sort of infinite realizations of getting a sample and then finding the estimate, then it would return on average the true value of the estimate, right, and if that happens it is very good and we get an unbiased estimator. So, as you could imagine, in statistics we like to work with unbiased estimators, right, because in this case it is guaranteed that the expected value of the estimator is near or equal to the actual value of the estimate. So, we prefer to work with unbiased estimators. So, in today's lecture we will look at several unbiased estimators for the population mean, for the population variance and so on. So, let us get started with our journey. The first thing that we will look at is called the sample mean. Right. The first thing we will look at is called the sample mean. The sample mean is an unbiased estimator for the population mean. Okay. So, given n measurements, constituting a sample, the sample mean is the arithmetic average of the values obtained. For the random variable. Okay. So, if the n values are denoted as x1, x2 up to xn, then your sample mean is given as 1 over n. So, I should use lowercase x 1 over n some I going from 1 to n xi. Okay. So, now why are we saying that this is an unbiased estimator for the population mean, which is capital X bar, right? You know that the population mean which is also denoted as mu is integral minus infinity to infinity x f of x d of x, right. So, this is actually the true value of the estimate population mean, which is the quantity that is being estimated. Okay. So, to really see that this is an unbiased estimator, we have to compute the expectation value of the sample mean. Okay. So, let us do that. So, the expectation of the sample mean is the expectation of 1 over n sum I going from 1 to n xi, right. And by the linearity property of the expectation operator, you can take the 1 over n as well as the summation I going from 1 to n outside, right. So, this becomes the expectation value of xi, right. Now, xi, right, refers to the ith measurement that is being made. Now, it is important to realize that each measurement is itself a random variable. With the same underlying distribution. Okay. So, what this means is that the expected value of xi will simply be equal to mu, right, because each measurement is a random variable with the same underlying distribution, right. So, this becomes 1 over n some I going from 1 to n mu. So, that becomes 1 over n times n mu, which is equal to mu, right. So, we have proved that the expected value of the sample mean is equal to the population mean. What this means in terms of the bias that we had defined a while ago, that the bias of x bar is equal to the expected value of x bar minus the true value of the estimate, which is mu, and we have just proved above that the expected value of x bar is mu. So, this makes the bias equal to 0, and that is why we call we say that the sample mean is an unbiased estimator of the population mean. Okay. So, this sample mean is very useful, right, when we are making inferences about the distribution that is being followed by a certain random variable. So, with that, let us move on to the sample variance. The next thing we are studying is the sample variance. Okay. So, the sample variance is used as an estimator for the population variance. Okay. So, this is defined as S squared equal to 1 over n minus 1 sum I going from 1 to n x I minus x bar whole squared, okay, where this x bar is something that we just encountered above. This x bar is basically the sample mean. The other important thing to note here is that the sample variance has 1 over n minus 1 in the denominator and not 1 over n, and it is this 1 over n minus 1 which ensures that S squared is an unbiased estimate. So, this S squared, the sample variance, is an unbiased estimator of the population variance. And that is the reason why we have n minus 1 in the denominator of the sample variance. And a more sort of physically motivated understanding of this factor of n minus 1 is because the nth sample measurement can be determined from the rest of the n minus 1 measurements and the knowledge of the sample mean which is required for defining the sample variance, right. So, the number of degrees of freedom in defining the sample variance is n minus 1, right. So, the factor of n minus 1 appears, right, as the number of degrees of freedom after defining the sample mean is n minus 1, right, because one equation is used up in defining the sample mean, right. Now, it is possible to define the sample variance without the factor of n minus 1, and it is done sometimes. So, that is denoted as S tilde squared, and here you have 1 over n sum I going from 1 to n x I minus x bar whole squared. This is called the uncorrected sample variance. It is an it is a biased estimator. So, it is a biased estimator of the population variance. Mind you, in Excel it is possible to compute both of these, right. If you take the square root of this, you will get the sample standard deviation and the uncorrected sample standard deviation. There is a function stdev which computes this particular quantity, and then there is the square root of this particular quantity, and then there is stdev dot p which computes the square root of the population variance. So, it is important to know what are the functions available in say Excel or Python or MATLAB, whichever is the programming language or tool that you are using, and it is important to know what exactly is going inside these tools. Okay. So, with that we can define the sample standard deviation which is quite straightforward. Now that we have defined the sample variance, the sample standard deviation is simply the square root of the sample variance. And again you do it so that the units that we get match the units of the random variable that we are studying, so that it becomes easier to get a sense of what is the magnitude, right, of the variation. So this is simply S is 1 over n minus 1 sum I going from 1 to n xi minus x bar whole squared, and you can also define the uncorrected, right, sample standard deviation, that is square root 1 over n minus 1 I going from 1 to n 1 over n xi minus x bar whole square, right. So like I said, in Excel if you use the function stdev dot p, right, the population standard deviation, right, this is the equation that is used, but if you directly use just stdev, right, in Excel this is what you would get. So it is important to be mindful of what is going on in our statistical tools or programming languages, right. And finally we come to a discussion of the sample covariance, right. Just like we defined the population covariance, we can define the sample covariance. Right, again we take two random variables for two random variables capital X and capital Y, right. If there are n data points, x1 y1 x2 y2 and so on up to xn yn, right, then you can define the sample covariance for this particular data set, right. Let us see how that can be done. So it is denoted as qxy, and that is equal to 1 over n minus 1 sum I going from 1 to n xi minus x bar times yi minus y bar, right. So let us consider the data set arranged in this particular manner, right, and we will get some insight into the working of this particular expression. Okay. So let us take the data points along the rows. So this is the first data point and the last row denotes the last data point. And in the columns, right, we will take the variables that are considered, right. So you can have x11, x12 up to x1p, x21, x22 up to x2p, and coming down all the way to xn1, xn2 up to xnp, right. So this is the first variable and this is the nth variable. So what we are trying to do is we have defined this sample covariance for two random variables x and y, but if we have an entire data set, which is what happens in machine learning, then how do we sort of generalize our understanding to this particular data set, right. So that is what we are looking at. So now for this particular data set one can define the vector of means, right. So now if you look at the expression for the covariance matrix, you have the means of the variables coming in there. So we have to compute the mean of each variable. So to compute the mean of the first variable, we will have to average over all these data, right. So that is n data points. To compute the mean of the second variable, we will have to average over this column vector, and to compute the mean of the last feature we will have to compute the average of this particular column vector, and in the end you will have an average value corresponding to each variable or each feature, right. So let us see how we can write this. So we have to write the vector of sample means. This is a row vector, right, that has the average of x1, the average of x2, and so on and so forth up to the average of xp. Now you know that you can write the average of x1 as 1 over n sum I going from 1 to n xi1. Then you can write the average of x2 as 1 over n sum I going from 1 to n xi2, and so on and so forth up to 1 over n sum I going from 1 to n xip. So this is basically the matrix the row vector of sample means, and you can clearly take out the 1 over n and the summation symbol. So what remains inside is xi1, xi2 all the way up to xip, right. And if you look at this carefully, right, xi1, xi2 all the way up to xip, that is basically right, you are summing over for over all the data points, right, and all the features. So let us finally see how you can write the expression for the sample mean of every feature. So x bar vector, that is essentially equal to 1 over n sum I going from 1 to n xi vector. Okay. So this is the expression for the vector of the sample means, that is a row vector, and we will go further and use this to simplify the expression for the covariance matrix. So this will give us essentially a row vector where each column is the mean of each feature that we are considering, right, and this is particularly useful when you are trying to write your own code to compute the covariance, right. So moving on, right, what we can do is we can define the sample covariances of all the features with all other features, right. So if you go up here, when we had defined it for only 2 random variables, then we were talking in terms of x bar and y bar. Instead here we will talk about each variable with the other, right. So instead of using x and y as the subscripts of q, you will actually use s, j, k, right. You are trying to define the covariance between the 2 variables whose index are j and k. So that is 1 over n minus 1 sum I going from 1 to n xij minus xj bar times xik minus xk bar, right, and j and k can be all the way from 1, 2, 3 up to p, because we just discussed that in this example we are looking at a data set with p variables. Okay. Now the interesting thing is you can make a matrix of these elements, right. These sjk can be arranged into a matrix, right, and because there are p features, right, or p variables, you will have a p by p matrix. So these entries will be S11, S12 up to S1p, S21, S22 up to S2p, and finally SP1, SP2 up to SPP. What is interesting to note is that this will be a symmetric matrix, right, because Sjk is equal to Skj, and the other very interesting thing to note here is that the diagonal entries are simply the variances of each random variable or each feature in your data set. So let us write that down. The diagonal entries are the sample variances, and this is a symmetric matrix. Since Sjk equals Skj. Okay. Now, how do you compute this matrix? Just like we were able to use vector notation to compute the row vector of all the means, right, of all the sample means, it is possible to use this vector notation to also compute the sample covariance matrix, right. So, this is essentially a matrix, right. So, this is the sample covariance matrix. And this matrix S, I will write it on the next page for clarity, can be computed as follows. This matrix S is essentially a huge matrix, right, where there is 1 over n minus 1 sum I going from 1 to n xi1 minus x1 bar whole squared, 1 over n minus 1 sum I going from 1 to n xi1 minus x1 bar and xi1 minus x2 bar, and finally the last entry will be 1 over n minus 1 sum I going from 1 to n xi1 minus x1 bar xi1 minus xip minus xp bar. And the last entry, the last row in this matrix will be 1 over n minus 1 sum I going from 1 to n xip minus xp bar xi1 minus x1 bar, and finally going on to 1 over n minus 1 sum I going from 1 to n xip minus xp bar whole square. Okay. So, like I said, this is a p by p matrix, and this can be obtained as 1 over n minus 1 sum I going from 1 to n, the product of one column vector, right, which is xi1 minus x1 bar xi2 minus x2 bar up to xip minus xp bar times a row vector, right. So, this is of size p by 1, the row vector is of size 1 by p. So, that is also xi1 minus x1 bar xi2 minus x2 bar and so on up to xip minus xp bar. Okay. And this can be written in a condensed notation, is essentially 1 over n minus 1 sum I going from 1 to n xi bar minus x bar vector transpose times xi bar xi vector minus x bar vector, right. So, all this we were doing just so as to obtain this very simple notation for the sample covariance matrix, right. So, now if you have a matrix of data, you can very easily compute what the sample covariance matrix will look like. Okay. So, this brings me to the end of this particular lecture. Here we discussed what the various sample metrics are, the sample mean, the sample variance, the sample standard deviation and the sample covariance matrix, and using these knowledge we will now go forward and enter into the realm of regression, specifically linear regression, and see how these statistical concepts are useful there. Thank you, and I will see you in the next class.